second substitution. That means when there is a substituent present already on benzene ring, we know that they are of two types, releasing, withdrawing. What next? That means when you have a releasing group already present on benzene ring, for example, when there is a methyl group, we know that it is activating. Of course, weakly activating. But still, when this is subjected to nitration, what happens? Now, see, all activators are no doubt orthoparadirectors. So, in this case, we get ortho as well as para products, right? Because methyl group is weakly activating because it is orthoparadirector, we get orthonitro and paranitro toluene, isn't it? See, this is toluene. Next, let us consider something which is withdrawing. Let me consider benzaldehyde. I mean aldehyde group on benzene ring. We know that this aldehyde group is moderately deactivating, right? Moderately deactivating. And of course, deactivators are generally meta directors, right? Except for halogens. Now, when this is subjected to the same nitration, the second substitution occurs at meta position. We get metanitro product, metanitrobenzaldehyde. So this is all about second substitution, which in fact tells us where the substitution occurs depending on the group that is already present. Depending on the thing whether the group which is already present is activating or deactivating. Okay. Now let us go for third substitution. In this case, we will already have two groups present on benzene ring and we'll be checking out the position at which the third substitution occurs. Going to be interesting. In fact, this is very important also. In this, of course, there are different varieties. Let me just go for this. when both are ortho-para substituents. I mean, when both are activators. Let me actually give you a methyl group and a chlorine, a halogen. In fact, halogen is deactivating, but is still ortho-para directing. Now, let us compare these two. Say, methyl group is weakly activating, right? Whereas chlorine is weakly deactivating, right? Now, in this particular case, activator dominates, right? Now, it is the activator which decides the fate of the third substituent. Okay, let's see. Now, let us take these two at three different positions and check what all we get. You need to be very cautious. Look at this. See, when you got methyl and chlorine at ortho position. Now, when this is subjected to nitration, you know, in nitration, as it is very clear from this discussion that the methyl group is going to decide the fate of the third substituent, right? So now let us check the things. We know that methyl group is anyway ortho-para. Of course, both are ortho-para, but still the dominating group here is methyl. So let us consider the methyl group and check what all are the available areas. Now, anyway, this ortho is blocked. Isn't it? You cannot get the substituent here. Yes, the other ortho is possible, and even a para is possible. Isn't it? You got two ortho and one para positions. You will normally have these two, but the point is one of the ortho positions is blocked. Now, I've taken the para one. This is one such possibility. Then the second possibility is this. Here, right? Now, these are the two isomers possible when we consider the two ortho-para substituents at ortho position to each other. Hope this is okay. Only two positions are possible, this and this. That's what I've given. The third substitution can occur only at those two positions. Next. Now, when these two are taken at meta position, let's check. Okay. Yes. When this is subjected to nitration, we are considering this. Now, yes, we have both the ortho positions and the para very much free. So let us write all the three products possible. The first one, of course, when you speak of the possibility of the formation of this product, this is very much difficult, because see, it has to actually get uh, attached in between two very big grooves. So if you consider the percentage, it will of course be very less, but it's a possible product. Then go for this. And finally this. Okay. Now this is how we get three isomers. When you got them at meta position to each other. Then finally when they are at para to each other. Yes. This is anyway the important substituent that decides the fate of the third one. You got the two ortho positions, right? Anyway, para is blocked. Now, when this is subjected to nitration, we get this, then, of course, this. But see the interesting thing. You know, it is like 1 to 4. If you go for the numbering, even this also is 1 to 4, right? They're all substituents. Like we'll just be giving the numbers based on the least sum rule. So when that is the case, though we have written two things, let me say that both are same. This needs to be concentrated seriously. They are same, and let me just consider that this type of an arrangement gives only one isomer. I hope this is clear. Now, finally, let me just give you the mantra. Now, the OMP thing actually gave us 2, 3, 1 distinct isomers, right? So that is the final mantra. you need to concentrate on. I think this is very clear. Thing very interesting is the last one. That is where you need to be, little careful. Now, the next variety. Now, let us take the second case. When both are meta-directing, I've taken cyano and aldehyde. Now, the strong one is cyano. The strong one decides the fate of the third substituent. Right? Come on. Again, three different cases. Hope you can imagine. Let us take the two at ortho to each other. Now, the thing is, cyano is going to decide what the product is. Nitration. You know, for cyano, this is a meta and this is a meta area, isn't it? Now, this and of course this. Now, these are the two possibilities. Check whether they are the same or not. That is up to you to see whether they are the same. If they are the same, take them as just one isomer. But here, as you can see, these are different. So, in this case, we get two isomers, right? Then let us take the meta and para ones. Now, when these two are taken at meta to each other and subjected to nitration, again, see, anyway, one of the meta positions is blocked. Another meta is okay. So just one isomer is possible in this case, right? Now the third one. Take them at para to each other. Now, in this case, we have both the meta positions available. This meta and this meta. Let's see. Yes. Now check whether these two are different or the same. No, they are same because anyway cyano group is senior. The carbon that has got this cyano group gets the first number, nitro gets the third number, and aldehyde gets the fourth number. I mean the carbon that has aldehyde. Same 1, 3, 4 even in the second case. So this again is only one isomer. Now the final mantra for such a thing can be given as it's 2 for ortho, 1 for meta, 1 for ra. That's it. Now let us go for the third and the final variety. When one is ortho para, the other one is meta. Yes. Let us consider the same old methyl and aldehyde. No problem, you can also take cyano, whatever it is. But the point is, the one that is ortho para or the one that is activator decides the fate of the third substituent. So this is activator, ortho para, whereas this one is a deactivator, meta. But being an activator, this decides the product. This is important. Let us take the three types again. Now, when this is subjected to nitration again, this group is very important. One of the ortho positions is blocked. You still got one more ortho and a para. Okay. para, and ardo. Yes, these are the two isomers, the distinct isomers possible. Now let us take them at the meta position. Now when this is subjected to nitration, as methyl group decides the fate of the product, fate of the third substitution, we have all three positions very much possible, very much available. Come on. First one, the second one, and the third one. Again, these three are distinct. So when they are at meta position to each other, we get three products. Now let's take them at para. Only the two ortho positions are okay, but the para is blocked. But check the interesting part. You can see that both are same. Starting from the carbon that has aldehyde, it becomes 1, 3, 4, right? So they are the same isomers, same and just one isomer. Now the final mantra. In general, when you have one ortho para and one meta substituents, this is a mantra. Okay. So this way, the two substituents present already on benzene ring decide the fate of the third substituent. When both are orthopara, in fact, the one which is more activating decides the product. And you get orthopara products. When both are meta, the one that is a strong, strong deactivator, it decides the product. And you get a meta product in that case. When one is orthopara and the other one is meta, no doubt, the orthopara one decides the fate of the product.